Good morning, everybody, and welcome to yet another lesson of CE 3372, Water Systems Design. And today is lesson 11, and this is our last lesson that has anything to do with EPANET, and there will be a homework placed. I'm still waiting for the software to download so that I can create the homework assignment. It started on Friday. It's only 5 gigabytes, but my house network isn't working so good. And actually, I've noticed over the last week or so, none of the networks are working good. But we will use, like I said, that will just be a routine excuse for the foreseeable future. And we'll make the best of it. So in the blackboard for this lesson is lesson 11, and today we're going to examine extended period simulation and a little bit of the water quality simulation features of the computer program. And then that would that's all the formal instruction on use of EPANET, and then from there on you'd be using the user manual in your own problem to deal with it. So taking the link to the page, that doesn't look right. Oh, and we have a cat that's going to join us. Well, hello, cat. Sure you don't want to go down there where it's nice and comfy? No, you don't, do you? That's here. Okay, that's surprising. So in lesson 11, we will start shortly, and I need to check that okay, that's not me. That is a cat doing all that. Seriously, you gotta keep your paw off that button. Yeah, thank you. And it should be all downloaded in a second. Yay. And I hope what I'm about to do next doesn't create anything worse. We go to data links. There should be, good, the files are there. This index page, I will update that as soon as we're done for today, because it has some parts in it that don't belong. And the lesson description. So lesson notes, lesson 11. You shouldn't have to re-download it. It should already be cached. There we go. So today is the storage and extended period simulation features of the program. So the examples they presented in the last couple meetings, in all cases, we were doing what are called single period steady state simulations. That is, we set up a set of conditions and we ask the computer program to compute the flows and the pressures in the network, and no changes were going on. An alternative and potentially more useful approach is to allow the demands to change from hour to hour over the course of a simulation, and to keep track of the filling and drainage of storage tanks or the evolution of water quality constituents in the network. So the water quality portion is of value when we're designing disinfection processes and want to locate where that's going to occur, so that we know the travel time of the disinfectant as it moves through the system. Alternatively, it can be used in a physical public security sense, in that we can simulate in the computer an intrusion of a contaminant and know how long it will take for it to get to a customer's connection, and use that as a way to design strategies to protect against that contaminant. And that happens more often than anyone can imagine. Flint, Michigan being a pretty good example of that, but it was not an instantaneous contaminant. It was a choice in changing water source. But in Milwaukee, in the last 20 years or so, it seems to me like the northern United States has really crummy water systems. It's actually because they're quite a bit older. They had a cryptosporidium intrusion into their system that was ultimately caused by a failed filtering system. Didn't fail hydraulically, it failed to do its filtering, and that introduced a pathogen into the system. And a tool such as this, had it been employed at the time, could have helped the operations engineers manage a recovery from that upset. And by manage a recovery, you might be able to isolate parts of the system, run the remainder of the system normally, and then just repair the isolated parts. So there's value in all this. So by way of overview, we're going to look at the tank model within EPANET, and we've done single period simulations, and then we're going to look at multiple period simulation. So all the materials that I'm talking about today are from the EPANET user manual. These two web links have nothing to do with today's lesson, so I don't know why they're there, except that I'm responsible. I put them there, but they don't fit the lesson. So I want to bring your attention back to an example from our last class meeting. And in that class meeting, we had this exact problem, and we were challenged with identifying the lowest pressure in the problem. I believe we came up with the lowest pressure was right here at node 3. And we applied our modeling protocol, which is to sketch the network layout on paper, identifying pipe diameters, length, roughness values, identifying node elevations and demands, and then identifying a supply reservoir or tank and supplying the pool elevation. Lastly, there's no pumps in this particular example, but we could identify pumps and provide pump curves. So we've gone through all that. The key feature here is identifying the reservoir pool elevation, and subtly hidden in this particular protocol is that this is for a single period simulation. Nowhere does it say identify demands and demand pattern changes with time, identify supply reservoir and reservoir storage conditions. That's not in this protocol. So by default, this is a single period simulation protocol. And again, borrowing from a previous lecture, here's how a tank is conceptualized in that particular example above and in general. And so in that tank connected to node number 2. So right up here. And it connected through this pipe number 8. And pipe number 8, we chose to conceptualize as having a total length of 300 feet, but more importantly, having a portion of the length, roughly 180 feet, that was at the same elevation as the node, 180 feet, that's coincidental. And then it went vertical for 120 feet to the bottom of the tank. So this tank is 120 feet in the air, actually 120 feet above the node elevation. And so the tank bottom is at elevation 300, and the tank has 15 feet of available depth. And so the maximum level in the tank is 315 feet above the datum. So that was how we conceptualized a reservoir. And we did that simulation, we got an answer. Moving into the extended period simulation concept, what we want to do is these programs are designed to find steady flow solutions only. So truly dynamic hydraulic simulation for a pressurized system is actually computationally challenging. And in general, there's very few free programs that can handle that because there's a significant wave equation component that occurs if we properly keep track of changes in flow. However, over many years, it's been discovered that a concept called extended period simulation, which produces a sequence of steady states, is a reasonably good approximation for things like water distribution systems. And the reason it turns out to be a good approximation is a change in the system propagates at roughly 5,000 feet a second. So a mile a second is how fast a change will propagate through a distribution network. That's the speed of sound in water. And within an hour or so, the systems will stabilize into their new operating conditions. And so we can leverage that observation in using extended period simulation. And then the only dynamic tracking we will do is keeping tracks of tanks draining and filling, because that doesn't propagate at 6,000 feet a second. And we can take the pressures at the beginning and end of a time interval, because those will equalize by the end of a typical time step. And then we can move pump operating points along a pump curve as indicated by the hydraulics. So extended period simulation is a useful approximation for how systems behave over time with comparatively subtle changes as time evolves. It doesn't do well for a sudden valve closure because you have condition before valve closure at steady state. You close the valve, you have a whole new steady state, and there's dramatic pressure changes in those instances. But other stuff like pumps turning on and off, tanks draining and filling are well within the computational capabilities of extended period simulation. Extended period simulation is used for various reasons, a few of which are listed here. One of the main uses is to model pressure in the systems during changing demands, typically at an hourly time scale. I suppose you could go to as short as 15 minutes. Much shorter than that, and you're introducing uncertainty with regards to how fast the pressure waves are moving back and forth. So let's stipulate that it's usually at an hourly time scale. And then whether we have actual demand data at anything smaller than hourly time scale, that in itself could be questionable in most communities. The second use of it, in conjunction with the first one, is to help us evaluate storage tank operations and if we've sized them properly. One of our concerns in storage tank design and operation is we want the tank to be large enough to handle those hourly variations. So if you recall back to the flow equalization lesson, we can specify an absolute volume of a tank as the sum of the two maximum deviations over a 24-hour drawdown period. And what we would want to do using the computer program is we put that tank into the system, expose it to the hydraulics of the system, and verify whether or not the tank indeed provides the necessary flow equalization. The third use of extended period simulation is for water quality. EPANET can approximate the water quality from multiple sources, and we can use it to evaluate things like the water age in the system, how old water is at different locations, old on the order of hours or days, and it's the age from the supply point. It can be used to detect intrusions into a system and assess the severity of contamination, or an impact assessment, if you will. And these seemingly unimportant activities are actually an important part of Department of Homeland Security, and there's a couple of versions of EPANET that are considered secure versions that you and I cannot easily obtain, but that are used for intrusion detection and impact assessment. And there's a nice variant called Winter out of Sandia Labs that's aimed at these particular questions. So the next topic is, how are these extended period simulations implemented in EPANET? They're implemented by a concept called a demand pattern. And what a demand pattern is, excuse all the nasal congestion noises. The cold front of the last few days has been a blessing in terms of temperature, but it brought with it all sorts of interesting allergens, I guess, if you will. My nose has simultaneously been running and clogged all weekend and most of yesterday. So we assign a demand pattern to a node. And what a demand pattern is think of it as a table of multipliers that the program will use relative to the base demand that we supply. So let's quickly visit this example here. So here we had a base demand of 500 gallons per minute. And so what a demand pattern would do is it would say, for the first hour, I'll multiply that value by 1 and I'll apply 500 gallons a minute to the node. For the second hour, maybe I'll multiply it by 2 and apply 1,000 gallons per minute to the node. For the third hour, perhaps back to 1 and 500. For the fourth hour, maybe 0.9 and operate at 450, and so on. So it uses this as a base demand, and it applies a signal to the base demand. And then once we establish a demand pattern, we can set simulation times, and this is we supply both the time step, hourly pattern, if you will, and how long we want the simulation to run for, total number of simulation hours, and then the program will follow the pattern repeatedly until it gets to the end of the overall simulation time. And so to modify our modeling protocol for extended period simulation, we simply just add this additional component, which is to identify the demand pattern and tank operating considerations. So here is an example, just a drawing and some annotations, and I'll explain them shortly. And these are the pipe characteristics in the example, and we'll go ahead and run this example in a little bit. So let's first look at the drawing. So this drawing has an elevated storage tank up here, another one here, and another one here. So tank 1, 2, and 3, if you will. And each of these tanks were supplied with the bottom elevation of the tank and an elevation storage table, which tells us for instance, if the pool elevation at one of those 3 tanks is 250 feet, then that tank is currently storing 200,000 cubic feet of water. If the pool elevation goes up to 260 feet, there's 250,000 cubic feet of water. If it drops to 240 feet, there's 120,000 cubic feet of water. Drops to 230, 40,000, 220, the tank is empty. There's also, in this case, 2 at-grade storage reservoirs. So these have fixed elevations that don't change with time. So these would represent very large volumes of water attached to the system. On the left side, at this left reservoir, the water is boosted into the network via a pump, which has the following operating curve. At 200 feet of head is shut off. At 190 feet of head, it produces 10 cubic feet per second. At 150 feet ahead, it produces 20 cubic feet per second. And then it's boosting into this network. And so the network is a network that we're already familiar with. And then here at the right side is another reservoir, also with a pump that I presume is to boost into the network, because it would be really stupid to pump into a reservoir. So the pump has to be boosting into the network. And its operating curve is 180 feet is shut off. 170 feet produces 10 cubic feet per second. 130 feet, 20 cubic feet per second. So that's our initial drawing setup. And then each of the numbered... Damn it! Hello? Thought that might have been somebody who didn't join the Zoom meeting. Get my brain back in gear. Got it. So each of the numbered pipes, in this case 1 through 27, corresponds to the pipes in this drawing. It has an upstream node and a downstream node. You can think of a starting node and ending node in the EPANET context. So for example, pipe number 1 starts at node 0, ends at node 1. So pipe number 1 starts at node 0, which must be this, that's not pipe 1. It's pump 1. I can't even find pipe 1. Must be the pipe that connects the pump into the network. Pipe number 2 starts at node 1, ends at node 2. Let's see if that makes sense. Pipe number 2 starts at node 1, ends at node 2, and so on. So here we have the table of connectivity, the pipe identification, the length of each pipe, the supplied diameter of each pipe, the minor loss coefficients, if any, on each of those pipes. And then let's look at pipe number, if I got that right. Pipe number 12 is showing that it's connected to a fixed grade node. So indeed it is. So pipe 12 connects to this tank. So that's what these fixed grade elevations are. We also have for each junction the junction elevation above a datum and the demand in gallons per minute. And here it looks like someone did it by hand to put them into cubic feet per second. And here's the gallons per minute divided by 7.48 divided by 60 seconds gives us cubic feet per second. So those changes are fairly straightforward. And now we want to go to how to produce a demand pattern. So if we take this chart, which I believe came out of the readings, probably Werbs and James, and we'll go back and check that in the readings. See if I can find that chart so you know where it came from. And it's so I'm a creative person, but I'm pretty sure I didn't take that chart out of any place I don't have documented. So let's see if we can find it. You actually can see where the example's coming from. So we're actually doing this example right now, example 419. So it's not in Werbs and James. Let's keep looking. If it's not there, then that would have come out of water distribution systems, maybe. Let's see if it's in here. The other place it came out of is Metcalf and Eddy, which I don't have copied and displayed. That's annoying. One other possibility that I have stored here would be possibly chin, but I doubt it. We'll take one more try and then I'll give up. Chapter 5 of the hydraulics book. Although the typesetting didn't look right. Oh well, it's not here. I will return to the actual presentation, possibly in my lifetime. Hopefully it remembered where it was. It looks like it did. So the likely source of this graphic, judging by the typesetting, was probably out of a Metcalf and Eddy wastewater engineering book, or a Montgomery Watson handbook for drinking water systems. I'll find the source. But let's suppose, for the sake of argument, we have information like this. So perhaps we have a maximum curve for some particular day, either in our actual system or nearby, or possibly in our guidance document. So this particular curve is based on an average day. So an average day would be this 100% line. So what this is saying on a maximum day is at midnight there's a drop in demand, and then in the morning there's a first peak and then a drop and then a second peak and then it returns back to midnight. Now it's not too hard to see that the area under that curve is certainly larger than the area under an average day. So a maximum day would represent the worst case for a system. And then on each of these hours, we're selecting points off the curve that correspond to a particular hour. For example, at 8 a.m., this curve says that there's 200% use over average on a maximum day, and at 8 p.m. we're at 300%. And we can go ahead and produce a multiplier table. So hour 1, 2, 3, 4, and so on. We have the various factors, and here they're shown as clock time. So at midnight, clock time 0, the multiplier is a 1. At 1 a.m., the clock time 1 a.m. second hour simulation, the multiplier is 0.9, 0.91, and so on. So we're taking that curve and we're replicating it as a table of factors. Once we have those factors, we can then go ahead and build our network. So we would lay out the network. We'd place nodes, junctions, tanks, reservoirs, links, pipes, pumps, and valves. Then we'd add the pump curves, and we do that in the browser. We select the data tab, we select curves, and then we would add type equals pump. Then we'd add the storage terms, which is in the browser, data tab, curves, and then we add type equals storage. And then we add the demand patterns, and that's in the browser patterns add feature. We'll do that live shortly. And when we've done that, we would have a interface picture that looks something like this picture right here. And here's what the demand pattern editor looks like. So when I go to the EPANET example, the actual live example, and upload these files, we'll go look at these things. And in that case, the demand pattern will have something other than ones in it. And the key thing is in the data tab options, dealing with times in the hydraulics, we have to make a few changes there. The default total duration time is usually a 0, and that's a single period or a snapshot simulation. And we're going to want to change the duration of the simulation to something other than 0 to take advantage of the time varying simulation. And here's the storage tank. It turns out that in this particular problem, the storage tanks don't have enough volume to actually find a solution. But if we add a extra volume, another 50,000, another 70,000 cubic feet of storage, these tanks will perform adequately. And then we would enter our demand pattern, and you can see that's taking the shape of the curve from which it was derived, and run the simulation. In the case of a extended period simulation, we get repeats of a lot of tables. So it gives us results at different times. So at the first stress period, here's all the pressures, demands, and heads. And then it tells us the storage tanks, whether they're filling or draining. And then it continues to the next time period and repeats. And you can tell whether it's filling or draining by the nodal results and the positive or negative sign with the respective object. At this particular time step, both reservoirs are supplying water to the network, which makes sense because they're attached to it by a pump. And all three tanks 1 and 3 are filling, while tank number 2 is draining. And it gives us the pump operation points. So lots of output. So if you're running short on numbers, this will make a lot of numbers. And in the quality category on these examples is showing up as 0 because we haven't activated the water quality feature of the program. So now let's actually go and run the program. I need to get the data links built. Actually, I want to do it from the remote program. So go to the home page and we go to EPANET in a box, and I hope it's running. I haven't checked it in a while. So far, so good. Attempt a connection. Okay, that appears to be running. Now the hard part, to get the data. I'm trying to do this the fast way, which is to download it. Oh, this didn't work last time. Why am I trying to repeat stupidity? Let's see what happens. Yep. And you're not going to work, are you? No, instant. Yeah, it's not going to work. Junky program. But I think I left the necessary script to do. Yes, we can do it with a wget. Let's first get to the correct directory. So I want to change directory to desktop. Okay, so we need some more examples. Let me see what's in these exercise 9, 10, and 11, because the examples may already be there. I just have them named incorrectly. Okay, that's a homework exercise. This is, we've done that one already in class. We've done that one in class. We've done that one in class. Okay, so none of these are of use to me. But we'll get this. So we're going to need to make a directory. Lesson 11. Let's just keep it simple. Okay, so now there's one, then we will change in that directory. Empty directory. Okay, good. Now we'll go ahead and set up the collection commands to get the data. So don't touch anything, and now I've got to go ahead and figure out what the actual data in lecture EPANET files. I want to take example L11 I hope this actually works. Oh, it's already gone into screw up mode. Let's see what happens. Nothing. Example -L010-1.net. L010. -1.net, okay. Let's see, 11. Data in lecture. EPANET files in lecture. Example -L010-1. L-11. Yay! And there should be a bitmap there also. So for you Windows users, you don't have to go through any of this crap because it's easy enough to drag and drop the files directly. No -1, okay. Yay. All right, so now in theory, we have everything. I think we want to go and get the other two. There's a L11-2. So let me go ahead and get that. So we're in lesson 11. Let's see if I can pull this all into the same directory. Okay, I don't need, I think the bitmap is the same. Sure enough, that was, can use the same bitmap. And then water quality is going to be example-water quality. I'm going to need this, even if I don't get to it today, we'll need this anyway. So let's go ahead and get that. Example-water quality. And we'll go find the file names. wqexample.net. Cap wq. Cool, and there's a bitmap, I think, by the same name. We will let that download in the background because its estimated arrival time is in 15 minutes. So now we have most of the contents that we need. So we'll do, there's two network files, there's a bitmap, and there's a water quality bitmap for that simulation. And hopefully this can handle the concurrent connections. Good. So now we've got the tools located. We'll start our EPANET simulation. And in the interest of time, we'll go ahead and we're not going to build the model live. We're going to go look at an already built representation of it. But we'll point out the features. So we'll do 10-1, hit open, and there's the network, and let's see if the bitmap is of any value. And you can see there's a sizing issue here. There's a technique called alignment where we can align the two graphics, but I'm going to give myself a little more real estate. Hopefully I don't regret that. My panel area. Okay, so here's our reservoir on the left, reservoir on the right, 1, 2, 3 storage tanks. Let me get back in select mode. Now I'm going to attempt to align the image just so you can see how to do it. And because I don't have the scales not correct, it's hopeless. Especially since we're doing it over the network and the network doesn't want to respond quickly. So we'll have to take it on faith that the network in the picture and the network in the EPANET are the same thing. If we go to full extent, that's not going to help. So I'll unload that. And there's our simulation. Let's go ahead and turn on some objects. So we will go into the notation. We're going to display the node IDs and the link IDs right now. And so now the numbers next to the links are identifying the various link, and the numbers and names next to the nodes identify the nodes. The pipe numbering is different than the picture because of the way these pumps are represented. So this pump is lifting, is boosting from the left reservoir into node 17 and then on into the network. And then the remaining nodes are supposed to coincide with the ones in the drawing. And then this pump is boosting from the right reservoir into the network, and we have the 3 storage tanks. We'll pull the browser on top and get it in the way, and let's look at options. In the times option, We're set for a total duration of 24 hours. I think if I put that as a 0, we'll get a 1-period simulation. Or I've just broken it. If we look at the storage tank, it has an elevation, an initial level, a minimum level, maximum level, a diameter, and it has a volume curve, so it's taking it volume curve number 3, which would be revealed in the browser, which is refusing to stay on top today because I have an audience, and a computer's job is to make a human look like an idiot in front of other humans. So that one corresponds to storage tank number 3, and if we look at the, I made a mistake, I want storage curve number 3. If I look at storage curve number 3, it says it's a storage tank depth above the tank bottom, and it has heights above the bottom and the various amount of water in storage. So I've turned off the multi-period simulation, and this should, when I run it, let's go ahead and look at the left reservoir. It's set at a head of 100 as in the problem statement. Right reservoir is going to be at 120. Just for grins, we'll look at node 2. Node 2 is at elevation 110, so it's 10 feet uphill of the pool of the left reservoir. So the only way water can get from the left reservoir to node 2 is it has to run uphill, hence the pump. And it has demand pattern 1, which if we go back to the browser that just hit itself again, thoroughly hit itself this time. This is why companies pay a small fortune for value-added interfaces, because they don't have to lose time doing this. I was looking for demand patterns, so we look at demand patterns. There's a demand pattern number 1 here. So this is a this demand pattern is not interesting at all. It says the multiplier is 1 at every time step. So if we run this, currently we have 0 changes in time. So I'll run the simulation. It says the run was successful. It returns this information here, single period. We'll go ahead and we'll put the pressures on at the nodes, and we'll put the flows on in the pipes, and that's a terrible color scheme. And so here's the result of our single period simulation. It says that the pipe 31 is adding water to the storage tank, pipe 30 is adding water to the storage tank, and pipe 29 is adding water to the storage tank. So if we were to look at the plot of, hope this will work, head in the storage tank, I think it should return a 220. Yeah, there's no information, so it can't do a time series plot. Now if we go back to our data object and choose options, we'll go back to times, and we'll turn this to 24 hours. So now it's going to do 24 simulations, each one an hour apart. And so the level in these storage tanks will be able to change. So reset the times, rerun it, choose OK. The first indication that it's a multi-period simulation is up here in this right-hand corner. It has a day and time stamp appearing. And so I will move the browser down here slightly. I'm going to click forward 1 simulation interval at a time. And I guess I want to direct your attention to the various numbers on the map. Let's make them big enough to see. Did everything but what I wanted it to do. That's funny. Let's drop those down a bit. Bring the nodes down to about the same size. Must be in notation. There we go. That's what I wanted to see. I want you to keep your eyes on these various numerical values as we step through time. So by default, it starts time at midnight. So at 1 a.m., here are the conditions at 1 a.m. in the morning. 2 a.m., you notice the pressures are not changing much, but the tank pressures are. So let's, in terms of node, let's change from pressures to head. We'll reset back to 0 hours. Keep your eye on the head in the storage tank. Let's look at storage tank number 1. So midnight, 250 feet of head. 1 a.m., 252 feet. 2 a.m., 254. 3 a.m., 256. 257, 259, 260. I think there's like 15 feet of freeboard in that, so at some point we're going to max out. 261, 262, 262, 263, 264. So it's slowly gaining water, and then in this case, these are all slowly gaining water. So let's change the time to a wee bit longer. Let's go. I want to get it to cycle. So let's see what happens if we go for 48 hours. Rerun the simulation. Choose the okie dokie button. So 48 hours, things are still filling up. We're not returning, but let's suppose we wanted to study a particular tank, say storage tank number 3. We can now plot a time series of, we'll put head in it for lack of being creative. Choose OK. So there's the head, or you can think of it as the pool elevation in storage tank number 3. We also could plot really, we don't have much other options. Pressure, I suppose. Pressure is going to look the same. And so that is an extended period simulation. Now in this particular instance, the extended period simulation is not terribly interesting, but let's see what happens if we reduce the elevation of the right reservoir. That's getting somewhere. So we drop that into the 90s. So I'm going to do the same on the left reservoir if I can find it. Naturally, it is off scale because... So effectively what I'm doing by reducing the reservoir elevations is I'm forcing the pumps to move at different points of their pump curves, and that's going to have overall effect on the entire network. So I run that. What I'm trying to do is get them low enough that this thing cycles. Almost. I will leave that be. Let me close that. And we'll open a different version. So this is the same. In this case, we can use the alignment. I think the scales are almost correct this time. Oh, I was dreaming. Not even close. I will unload. This is essentially the same example. Let's see what the changes are. Storage tanks look the same to me. 120, 100. Don't actually know what the difference is. We run it. This one has the tanks draining and filling. So I've made some subtle changes in the network somewhere so that the tanks will cycle. So if we let the simulation animate, you notice the storage tank is filling, then it's starting to drain again. Filling, draining, and filling again. So I'll stop that. Let's make a bit of a change onto options. So we'll run this for 96 hours. That should be a good long run. Hopefully that won't crash it. And we just crashed it. Negative pressures at 44 hours. So we will go back to it goes negative at 44, so let's run it for 36 hours, day and a half. So if we now pick a tank, and we will plot the total head in that tank, we see that the tank fills up and then starts to drain and then gets a little bit more fillage and then drains and then fills up but not quite as far this time and starts to drain, and then eventually we get to where we can't sustain the pressure in the system. And let's see what happens if we can let's really crank that pump up. So we will double its speed. We'll double the speed of this one. That should make those pumps work a little better. And I just filled that tank up and it stayed filled. So doubling the speed of the pump was not the brightest idea. So what I'm trying to do for demonstration for the class is I'm trying to set conditions so that we can get cyclic behavior. But clearly that's escaping me right now. Try that one. Warning message, so that is a little bit too much. We'll boost this pump too. Okay, good. So what I want to do is extend the time period so we can get better temporal plots. And plus, a real network, when you've designed it or are operating it, ought to be able to run for more than 36 hours before you have negative pressures in the system. If that's not the case, it's indicating to you by analysis that there's something wrong in the design and you would have to systematically find things to fix. If it's already a real network and the simulator says it won't run, but the real one's working fine, then you have a conceptualization error in the hydraulic model. So let's go for a full 96 hours and see if I can get it to work. Sweet. So we may have actually got the cycling that I'm after. Let's look at the, well, either got the cycling or the tanks are all filled up. Yeah, tanks are filled up. So let's back off on the pump performance just a bit. That was too quick. Gonna get the same behavior, aren't we? Okay, that's kind of what I was going for. So what I would infer from this graphic is that if everything else being more or less, in our opinion, correct, our tanks it spends a lot of time full and then it's drawn down a bit. So I'm intentionally putting imbalances in. Let's go ahead and run the animation briefly. Filling. Yeah, the tanks are filling a bit too fast. So let's drop this down. How about stop? All right, that's the best I'm going to do in the time we have right now. And if we go ahead and look at the tanks, so fill, drain, fill, drain, fill, drain, fill, drain. And what I was doing was jacking with pump curves. And that's how extended period simulation is useful in hydraulic design, especially if we get cases where the tanks drain too easily. Let's go ahead and check volume curve number 3. Let's change one of the curves. So if I change probably don't want to change that. Cut and paste isn't working. I want to create another volume curve where the tank doesn't have as much volume in it. I guess I can do that right now. I'll take out this 50 and nothing will happen. Oh, it's gone into disobedience mode. Well, okay, this is a good time. We will go ahead and terminate the program. Wait to get EPANET comes up here. Wine server, there we go. 3056. Trying to regain control of my computer. GWE 94 something. 9498. Yay. Okay, so that was introduction to some extended period simulation. Now let's see what the time we have left. We got about 10 minutes, a little less. We will get started on water quality if I ever get back to here. So the water quality portion is a pretty advanced feature of the program. Interestingly enough, a lot of people don't actually know about it. And what it does is it gives us the ability to introduce a constituent in the computer at a supply point and track its behavior as it moves through the distribution system. So the underlying theory is advective transport in the pipeline and then different kinds of decay reactions that are built in within it. And in practice, it's used to estimate the water age in the system, estimate concentrations of constituents at different points in the network, and come up with strategies and tactics to respond to intrusions into the system. A quick look at the transport theory is by a technique called discrete parcel advection, and then we'll look at the mixing approach in tanks. And in terms of transport theory, we have at least 2 entire graduate classes in it, and so I'm not going to be able to come anywhere near doing justice to that in the few minutes we have together. But I will mention that advection is the transport of dissolved or suspended material by motion of the host fluid. For example, when you get into an automobile, if you consider the automobile itself to be the host fluid, you are advected because the automobile moves. To describe advective transport, we have to have knowledge of the velocity field. And velocity, as you recall, is both speed and direction. In the case of a hydraulic network, we know the direction because we created the network, and then the speed is relatively easily computed from the network hydraulic equations. And the velocity that's used in contaminant transport computations in EPANET is called the mean section velocity. And this picture here is an attempt to graphically describe what the mean section velocity is. Visualize, if you will, a portion of pipe that is L units long and has a cross-sectional area of A. So the total volume of liquid inside that pipe is L times A, and we'll presume it has a flow rate of Q. So now visualize that same portion of pipe. Initially, all the liquid inside the pipe is red, except for this point right here, which is magically labeled green. And because it is advective motion only, there's no diffusion. The green doesn't dissolve into the red doesn't dissolve into the green, and at zero flow, the red isn't going to dissolve off to the right. If we choose a time stepping scheme where the total time step is equal to the length times the area, which is now the volume of that portion of pipe, divided by the flow rate, this delta T represents a hydraulic residence time. So now let's watch how our system behaves over time. If we let 2/10 of the hydraulic residence time elapse, we will appear to see the green dot move roughly 20% of the way to the outlet. And this portion of red has displaced into the next section of pipe. If we let 4/10 elapse, we have 40% of the distance is traveled to the outlet, 6/10 60%, 8/10 80%, and 10/10 we've completely cleared the pipe of the red-green markers. And so the apparent speed of this green marker is it's displacing in space over a known time interval. That speed is the discharge divided by the cross-sectional area, and that marker velocity is called the mean section velocity. We can extend this game a little bit where we can have a portion of pipe of interest right here, and we're going to examine as different materials come at it. And for example, in this second line right here, if 0.5 hydraulics residence times has elapsed, this pipe is half full of what was there and half full of this light blue material. And then at 1 hydraulic residence time, the entire blue material has made its way into the pipe. And we could repeat that with green and red. And we ultimately come up with the same expressions here. The amount of blue that's in the pipe is equal to the volume of the pipe multiplied by the concentration of blue. And the change in the mass of blue entering the pipe with respect to time is equal to this ALC blue times Q over AL. And if we divide out the necessary terms, we have the mass entering per unit time is whatever the concentration of blue is times the flow rate. We use those ideas with a mass balance in a small portion of the pipe, and we look at the entrance and the exit side, and we can write a mass balance that says the mass flow in is C1Q1, the mass flow out is C2Q2. If Q1 equals Q2, they can be collected. And the rate of accumulation in the segment is concentration times the area times the length of the segment. And a little bit more algebra, and we can ultimately come at the advective concentration equation for our segment of pipe, which simply says that the spatial variation of the product of mean section velocity and concentration is equal to the time rate of change of concentration in the pipe segment. We can generalize that to higher dimensions than just the pipe, and the last term is usually isn't always written like this, but essentially it says the time rate of change of concentration is equal to the negative divergence of mass flux. And to understand these mass fluxes, we have to understand velocity, which again in EPANET is easy. Let's see, skipping over this. I didn't know it was going to even render any of this. There's where I want to get to. So the whole point was to explain this single 2 sentences in the user manual. EPANET's water quality simulator uses Lagrangian time-based approach to track the discrete parcels of water as they move along pipes and mix together at junctions between fixed length time steps. The water quality time steps are shorter than the hydraulic time steps, minutes versus hours, to accommodate the short times of travel that occur within pipes. Then when we get to a node, we have mass flows from the various links connected to the node, and simple mixing is used at the node, where you sum all the masses coming in and you divide it by all the flows coming in, and that becomes the concentration at the node, which is going to flow out to its next node. Within tanks, there are 4 possible tank models: completely mixed, 2-compartment mixing, first in, first out, and last in, first out. Completely mixed is the one that we commonly would mentally associate with tanks. Once material gets into the tank, it magically completely mixes uniformly throughout. It's a reasonable approximation for physically small tanks, or for tanks that have a fairly long hydraulic retention time compared to the transport time steps. 2-compartment mixing breaks that tank into 2 zones, an inlet-outlet zone and a main zone, which conceptually the inlet-outlet zone its storage is satisfied before material is transferred to the main zone and back again. This might be useful for very large tanks. First in, first out mixing is classic plug flow reaction. So the parcels of water that enter the tank first are the first ones to exit. And so it's essentially plug flow in the tank like you had in your environmental engineering class. And then last in, first out mixing is a good mental model for stratified flow in the tank. So as material enters the tank, you can think of it as pushing these layers up, and then as it leaves, the layers come back down. And so the last component in is the first component that comes out when the flow direction changes. The reactions that are built into the program are bulk reactions, so that's in the main liquid phase, and reactions that occur at the wall and a boundary layer within a wall. So this diagram is showing iron oxidation reactions at the boundary layer and disinfection reactions in the bulk fluid. And there are 4 different kinetic models that are provided in the program: first order decay, first order saturation, zero order kinetics, and then no reaction, which is a tracer. You can think of that as a tracer model. And then the wall reactions are handled in a similar fashion. So here's an example that we're out of time for today, so I will show the example and we'll pick it up next time and then move on into drainage design. So this example, we have a supply point up here at 3 cubic feet per second, and we're told that the source water has 10 milligrams per liter of a disinfectant, and we're given the first order mass transfer decay coefficient, and we want to find out what the disinfection residual in the system is at different locations. So to model that, we would create the model, just like an extended period simulation model. So for water quality, it has to be extended period simulation. And in the case of the demand pattern, it would be just a flat line demand pattern, all ones. And then run the simulation, turn on the reactions, supply the reaction order, the bulk coefficient, tell it it's first order, zero out the remaining terms so that they don't participate. Select the times. You notice the hydraulic time step and the quality time step are 20 times different in value. So let's see. So 5-minute time steps for water quality, 1 hour time steps for hydraulics, pattern time steps provided, and so forth. And then we'll go to our reservoir and we'll set its source quality at 10 units of concentration. There's a few other tricks that can be employed on the constituent tracing. In this case, we're just setting it at the source editor. And then we're telling it that we want to get the chemical response at the node and run the simulation. So what it's telling us, we have 10 units at the source, and we get over to this corner, we have 4.12 units left, and this is after 24 hours of simulation. Generally, the mass can't get from one end to the other end of the network in a single hydraulic time step. So when you run these simulations, if you run them for each hour, you'll see these numbers start to grow, and then they hit a steady value when they've hit their localized equilibrium. And 24 hours in this case is more than enough time to reach an equilibrium for this extreme node. And so if our regulatory guidance for this particular constituent, let's say it's supposed to be 5 units or larger, we get a 4.12, we would conclude, well, we either need to increase the dose here at the source or somehow get water here faster so it hasn't had enough time to to decay down to 4.12. Some additional concepts is we can use tracers to estimate water age in the system. It's just another constituent. We use a zero order reaction with a bulk coefficient of 1, and the resulting concentration is water age in hydraulic time steps. It's possible to use multiple sources to estimate mixing in a system, and we can do contaminant intrusions by injecting a dose at a node and seeing where it arrives. So here's an example doing water age. So in this case, the water is 4.22 hours old when it gets to that node. And where we're headed on our next meeting, we will start open channel flow. So we're about to leave pipeline pressure systems. There's one more homework that I haven't posted because, again, the software hasn't completed downloading so that I can render the assignment. But it's going to be an EPANET assignment. There'll be at least 2, maybe 3 questions. The first one is going to be a very simple network. Build it in EPANET, run it. The second one is going to be to take the Somewhere USA network and put that into EPANET and run it. And that one you need to save because that's going to work its way into the class report. So if there's no burning questions, I will end the phone call for today. And so that seems like a burning question. When's the first exam? I'm going to try to get the first exam programmed into Blackboard this week. And then I have to test it to be sure it actually works right. And so you can expect it by the end of the week. And my goal would be to have it posted on Thursday, and you have the entire weekend to work it. So that answers one question. All right. So I'm out of time, and I want to thank you all for your patience putting up with my network not working the way I want it to, and my rather dry voice because this is my 4.5 hour of lecturing by the time I get to you all, so I'm pretty whipped. And I will see you on Thursday. There are no outstanding quizzes. There's no outstanding assignments as of right now. There will be an assignment posted Thursday, and like I said, I'm going to try to get that exam posted in time for you to have a whole weekend to work on it. You still have multiple days to work on it. I'm not that evil. But with any luck, we'll get it by this Thursday. So have a great day, everybody. Have a good afternoon. The temperature's kind of beautiful outside. I hope you all get a chance to enjoy the outdoors a little bit. And take care, be safe, all the usual admonitions that we make in this day and time. Goodbye.